Okay, so obviously not all the time are we dealing with a bearing that has sufficiently low load that we could assume that Petrov's equation comes into play. Most of the time, instead, we're dealing with relatively high loads, because realistically, that's what we use lubricated bearings for. If we're talking lower loads, then we're probably going to end up using a roller bearing of some type anyways. So we're going to have that wedge formation going on. So essentially what we're doing here is zooming in on a tiny little square of fluid in the material. And we are summing up the forces in the x direction. So there is going to be essentially a pressure component. So an initial pressure component. So the pressure times the cross-sectional area in that plane. And then essentially the pressure on the other side. So which they're equating to this pressure plus some differential. Then on the bottom faces, we got shear stress going on. So we got a certain amount of shear stress, and we got the same amount of shear stress in the other direction, except we expect that there's going to be some sort of shear gradient. So there's going to be some sort of difference in the shear there. So go ahead, add all that up. Essentially what happens is this cancels out with this, and let's see where we. This cancels out with this, and we're left with dp over x times dx dy dz plus d tau over dy times dx dy dz. Obviously, the volume of that little cube, dx dy dz, cancels out. So we are left with just the pressure gradient is equal to the the pressure gradient times dx is equal to the shear gradient times dy. From there, we can make some substitutions and some assumptions and solve for what's going on in terms of allowing us to basically figure out flow rates and such. So again, the shear gradient is going to be a function of the velocity gradient. So that'll be our UH term here. And then boundary conditions are going to be that obviously at the top, this thing's rotating, so so the fluid is going to be matching its rotation at that top, and then at the bottom, the bearing side, the velocity is going to be 0. So once there, once there, you can basically solve for the flow rate, or the velocity, basically, the velocity at any particular point in the height as a function of the velocity of the journal at that point, the gap, and gap comes up there too, and the pressure gradient. So if we have the velocity kind of in that direction at any point, well, we can figure out what the flow rate is, because basically we've got that that flow rate, got the velocity moving in a particular direction, and then taking that, multiplying it by the kind of a height term, and integrating from zero to the from the bottom to the top allows us to solve for what the mass flow rate will be. Then we need to make a few kind of assumptions. The one assumption we can make is that the change in the flow rate in the x direction, so in kind of in the direction of flow, is equal to 0. So that's basically us saying that all the fluid that goes in makes its way to the other side. So there's basically no leakage kind of in the axial directions. So from there, we can solve for kind of what the pressure is going to be doing in terms of the velocity, the gap, so on and so forth, all at the various points. So that's basically assuming that it's a kind of an infinitely long bearing. And so if it's long enough, there's not going to be any room for stuff to leak at the side, basically. Or that, there might be a little bit of leakage at the very ends, but it's not going to affect what's going on in the middle. The other assumption is Ovick's short bearing approximation, which is basically the opposite. That is basically assuming that of the fluid that kind of enters from the top here, by the time it gets around, all of it leaks at the side. So we're assuming it's a very short bearing because we're all the fluid's leaking at the side. So that gives us different behavior. So generally speaking, Ovick's short bearing approximation is reasonable for bearings that are less than 1/4 the length of the diameter. Like its length to diameter ratio is less than 0.25. Above that, half and above, the long bearing approximation is reasonable. So anyways, this will lead to different distributions in the film pressure. So you'll get like the average film pressure basically needs to be equal to the load divided by the area, the projected area. So that's our average film pressure is equal to the bearing pressure, basically. The film pressure, it's obviously distributed at certain points. So it's going to be, it's going to start off small before that wedge starts to form. And then that wedge will start to form. It'll start squeezing stuff into the wedge, and the pressure will increase. It'll increase, and then eventually it's going to start to decrease. So this leads to those approximations we mentioned led to the ability to make certain assumptions that lead us to the ability to kind of calculate how these bearings should act under those conditions. So what they do is, again, we're doing dimensional analysis. So the bearing characteristic number is what's going to be given as the here we go. The bearing characteristic number is going to be what's given as the x-axis on all these. So that's given as S, the Summerfield number, I believe it's called. I'll double check that later. But that is equal to the the radius divided by the radial clearance squared times the viscosity times the rotational the rotational rate. Again, that's in revolutions per second, and the p-value, the projected the bearing pressure. So the load divided by the diameter times the load divided by the diameter times length. So all the units cancel out to a dimensionless number for that, and then that leads to other dimensionless numbers. So based upon any given bearing characteristic number, what we get is a minimum film thickness given as the H naught divided by C, so like a ratio of the minimum film thickness for these particular length to diameter ratios. So again, if we're working with 1/4, then that's we're making the short bearing approximation, not so much here. And that also leads to there's kind of an area that can kind of be described as the optimum zone. And that's basically the boundary between when we have the maximum load for a particular bearing and the minimum friction for that particular bearing in those operating conditions. So for any particular bearing, you're going to have the length to diameter ratio be constant, obviously. So you're following these lines back and forth. And as you change the Summerfield numbers, or the bearing characteristic numbers, you're gonna have you're gonna be changing the minimum film thickness variable. So our film thickness will start out, our minimum film thickness will start out small, and it will increase. And then kind of at this point, that's the bearing characteristic number that corresponds to the minimum friction. And at this point, that's the bearing characteristic number that corresponds to the maximum load that can be carried. So there's other characteristics we're worried about too. Coefficient of friction is one of them. So this chart here gives us in terms of our bearing characteristic number, for the different length to diameter ratios, our coefficient of friction variable. So that variable is R over C times the coefficient of friction. So it's very important that you double check exactly what it's saying there on the side. Next up, for the maximum film pressure, that is basically given as a function of the pressure divided by the the bearing pressure, so our p-value, divided by the maximum pressure that we see in the fluid. So it's gonna if we have a particularly high value here, then basically that's stating that pressure isn't spiking very much. Whereas if we have a particularly low value, then basically that means that when we solve for our Pmax, that'll be relatively high compared to our gauge pressure there. Compared to our bearing pressure there. Next up, the position of the minimum film thickness can be important. So this one's just given in degrees. So again, if we're rotating like this way, starting off at 0, we're starting off at 0. This is kind of the shift in the direction of rotation. So when we're at rest, obviously the minimum film thickness is at the bottom because it's sitting there, sitting there with metal on metal contact. As you speed up, the position of the minimum film thickness kind of shifts in the direction of the rotation. Next up, the maximum film pressure location and the film termination. So just let me zoom in real quick here. So the solid line here is the line for the position of the maximum film pressure, whereas the dotted line is the film termination position. So it's basically kind of where the pressure drops off to 0. So again, all that a function of the bearing characteristic number, and this is given in degrees. So what we've got here is a flow variable. So this flow variable that we got here, that's Q divided by R, C, N, L. So unit-wise, we've got R times C times L, length times the length times the length of volume, and then the N's in per second. So that gives us a volumetric flow rate, and up top, a volumetric flow rate. So everything cancels out nicely. So this is basically how much fluid, how much hydraulic fluid is flowing in to form the wedge based upon our characteristic number. And the bearing geometry, of course. Next up, we've got the ratio of the side flow to total flow. So for the side flow, if we have an infinite L over D ratio, then you don't get any side flow. There's basically nowhere for the flow to go. If you have something less than that, then some of it's going to make it kind of recirculate around, some of it's going to flow at the sides. So for a higher length to diameter ratio, we get more side flow. And for a lower speeds, we get more side flow. So basically, as you speed up, kind of there's more impetus for the flow to get dragged all the way around. Same thing if it becomes more viscous. It's basically kind of more likely to stick to the rotating instead of get squeezed at the sides. So yeah, those are the charts that basically you'll be using to kind of optimize the performance of your bearings. So we'll talk about how to do that in a